Hi, I'm Julia,
And I'm Eric.
and we're both educators in the Current Science and Technology program at the Museum of Science.
And this is the Do-It-Yourself Smell Bar. We'll be talking you through all of the activities that we have for each of the three segments. Today we're talking about chirality. Those are mirror image molecules.
We have an approach where there's three sets of activities for this topic. We start with the cognitive ramp, where people access the topic through things that are really familiar.
We have an activity for chemistry, so something that is introducing the public to molecules and how they relate to what we're talking about, and especially having something that they can smell as part of the smell bar. And we finish up with why we care about that. So what real-world applications does this concept have that you might encounter in your everyday life? So let's get started with chirality. So the cognitive ramp portion is the start of any smell bar. It really introduces the guests to the concept that you're trying to get across with familiar everyday objects. So we have both objects from nature and man-made objects that are chiral, which means they're mirror images of each other. The most common example of this is hands. Hands have what we call handedness. There's a left hand and a right hand. They can't go on top of each other. They're always different. They're mirror images of each other. If you take your left hand and look in a mirror, it looks like a right hand.
And here we have some other objects from nature. This is a set of ram's horns from the museum's collection, but you don't have to have that. You could find other kinds of horns and antlers, maybe. But this is, instead of seeing hands or feet, we're seeing the handedness of the spiral direction of the horns. So there's this side is called a right-handed spiral based on the way it grows. And the other one is not identical. It's a mirror image, and that's a left-handed spiral. And we've got some examples here with seashells, too.
So these are often the items that will bring people in, and you can explain what the concept is using them. And then we go from examples in nature to examples that are man-made. For example, scissors. If anyone's ever tried to use a left-handed scissors that's not left-handed, it's not very comfortable. It doesn't really work very well. You have to pick the right one that goes with the correct hand, or else it doesn't really work because our hands are mirror images. That's why you need two different gloves, many gloves, not all of them, but winter gloves and a lot of dishwashing gloves. So you can't put a left glove on your right hand. Shoes are the same way. A good example we use all the time, especially for younger visitors, is have you ever put your shoes on the wrong feet? And they say yes, and it doesn't work out because your feet are mirror images of each other. Your feet have handedness.
So now that we've established mirror images on this familiar scale, we're going to move on to molecules. And now for the chemistry activity in this smell bar. We're still talking about mirror image structures and handedness, but this time with molecules. So we're going to start with these little models that don't represent any particular chemical, but when we show these to visitors and ask if they're identical, sometimes the visitors say yes, but then we ask them to take a closer look.
So it looks like they're exactly the same. They're made of all the same components, but you can't actually lay one on top of the other and get the same exact result. They're always a little bit different. So you can't change it, you can't move it, you can't rotate either one to be exactly the same as the other. Because in fact, they're mirror images. It's like it's looking in the mirror. So when this one has the blue on this side, it has the corresponding blue on the same side. It's the same as if we took just one and used a mirror. So we actually do use a mirror in this case to show that this one in the mirror is the same as this one in real life.
These simple little molecules also are a good way to see what determines the chirality of a molecule. So usually a chiral molecule has carbon in it, and the chiral carbon is a carbon that is attached to 4 different atoms or functional groups. How the chemists decide whether they'd call this right-handed or left-handed just depends on rules that they follow, focusing on that chiral carbon and then looking at the groups attached to it. Okay, so that's just a pretend molecule. Now we'll look at a model of a real chemical.
So we have 2 models of carvone, one of each type. There's left-handed and right-handed. So they look extremely similar to each other, but there's a subtle difference where they're actually a mirror image. and that can affect the behavior of the molecule. We often keep them inside these clear containers if we have a busy day and a lot of guests because they are fragile and they break apart. But the behavior of the different ones can affect things like how they smell. So these two molecules, even though they're made up of all the same components and they look exactly the same except for tiny differences, they smell completely different. So we have Carvone here in these two bottles. One thing to keep in mind, especially with younger visitors, is to give them a little bit of instruction on how to use the smell bottles. We don't want anyone to put the bottle directly in their nose, so keeping it to the side and giving it a gentle squeeze and a waft is good enough to get the smell.
All right, I have the left-handed Carvone.
And this is the right-handed one. And this one smells a little bit like spearmint.
And this one smells like caraway, the spice caraway.
So people are often very familiar with spearmint. It smells like lots of minty gum or mints, and they recognize that scent right away. People will often say that they don't recognize the smell of caraway, but it's definitely different. So if they don't right away know that caraway smells a little bit like rye bread, they will at least say that it's completely different from this. So we took Carvone and put only left-handed molecules in one bottle, only right-handed molecules in the other bottle. The result is that they interact with our nose differently, and they smell completely different. Two other really good chemicals are the limonene. So we have the right-handed limonene. It smells a little bit like citrus.
And the left-handed limonene, a lot of our guests say it smells like pine sol. So it's a little more piney and kind of reminds them of a cleaner.
So having these actual scents that people can try out really reinforces that just the tiny differences in the molecules can mean a big difference in terms of how they smell, how those molecules behave when interacting with our nose. The last part is why we care about this. Just because two things smell different doesn't mean it affects our everyday lives. So we talk about how chirality can affect things that we might use every day. So we've talked about chiral molecules, how they're mirror images, how that can affect how they smell, but it can also affect how they interact with our bodies. And that is the real reason why we care about this a lot, how it affects our lives every day. Talking about medications that we use that might be chiral, which means there's a molecule that has both a left-handed and a right-handed version that might do different things within our bodies. One example of that most people are familiar with is ibuprofen. One side is a pain reliever, which we use. The other side is inactive. So it doesn't interact with our body in any way. So we don't have to separate that. We don't have to make sure that we only have one side or the other. Another example is the drug thalidomide, which was used in the 1950s as a morning sickness pill. And that was a pill that was a really great morning sickness pill on one side. The mirror image of that caused birth defects. So there were lots of children born in the 1950s that had birth defects because their mothers had taken this drug. So we really need to understand both sides of a chiral molecule before we can say for sure what it's going to do to the human body.
We have lots of other examples of chiral molecules in medicine. So here's one, the antidepressant Zoloft, that happens to be only the left-handed version of this chemical is the active ingredient in Zoloft. And here's a cholesterol-lowering medication that lots of adults take, Lipitor, and the active ingredient is only the right-handed version of that molecule.
So we can also use this in forensics. In example, a drug like cocaine has a left-handed version, which is found in nature, but when it's made synthetically in a lab, it's both left-handed and right-handed versions mixed together. So we can use that information to try to trace a sample, maybe identify it, match it with another one in a court case.
We've noticed that a lot of our guests are familiar with some of these medicines, might even be taking them. For example, Prilosec is a really popular heartburn medicine. It's made of both the left-handed and right-handed versions of a chemical. And the newer Nexium, same chemical, but only the left-handed version. And some patients find that that works better for them. So this and many of these other medicines trigger conversations with our visitors where they really can engage with the material because they have their own personal experience to offer.
And it's often very surprising for them to find out that many of the chemicals that we use as medicine have a left-handed and right-handed version. So having them understand the chirality, how the molecular properties can affect the behavior, then lets them figure out that some of their medicines can be affected by this very same principle. So it really turns into a conversation back and forth about the medicine that gets them to really understand why all of this is important in the first place.